Om Sahanavavatu Sahanao Bhunaktu Sahaviryam Karavavahai Tejasvinavadhitamastu ma vidvishavahai. Om Shanti Shanti Shanti. Om Samasta Jana Kalyane Niratam Karunamayam Namami Chinmayam Devam Sadgurum Brahma Vidvaram Sadgurum Brahma Vidvaram. Hariom. In this session, we'll just quickly take a tour on ancient Indian mathematics, and then we will see the introduction of Lilavati. So these are a few things that we can, you can just have a quick comparison on a few discoveries which was made in the West as well as in the East. So we learned about calculus that Newton or Leibniz had discovered calculus in 17th century, and we had Madhavan, a mathematician from Kerala, who discovered the same thing in 14th century. And this is now accepted by the whole world, like all these discoveries were made by Indians long before the West. So you can see again algebra 13th century, we see Bhaskara I talking about the same in 7th century. So we can see a lot of like Pascal's triangle or a binomial theorem, that entire thing we can see going back in Pingala. So we are going back 2 millenniums in fact as compared to the West. So like this, if we take any topic in mathematics, except for a very few, like if you talk about conic sections, hyperbola, parabola, ellipse and all that, coordinate geometry and logarithms. So except for these three, for every other branch in mathematics, we can find a discovery in India much before it was discovered in the West. So these are a few things which I thought I would just share, and a few other discoveries, significant discoveries by Indians, which actually gave a big leap to mathematics in such as, like, of course we all know zero and infinity also. So it is only because of this lack of conceptualizing zero or infinity that the Greeks could not venture ahead, it is said, because they could not conceive of zero as a number and the concept of infinity. Otherwise they were really good in mathematics. So why even though they were really good in mathematics, why couldn't they progress further? So it is because of this particular thing, zero. And of course we had a decimal place value system right from the Vedic period, like all this, all you Sanskrit students, you must be familiar with all these verses from different Vedic literature, like which talk about ekam chame, dasham chame, like all the powers of 10 and all. So that itself shows that at that particular time we had a decimal place value system well in place. Whereas the other civilizations, they were mainly using symbols for representing numbers, Roman symbols, Greek symbols, Babylonian symbols. So they had just symbols, but they did not have a place value system. So if we can just go a little deep into that, we can represent xii as 12. So using Roman numerals, we can represent the number 12 and we can represent the number 6. But we cannot do an operation by digit. How will we multiply using Roman numerals? Right? So we don't have a digit by digit multiplication in symbolic representation until we have a decimal place value system. So here we can do 6 into 12, 6 and then 7. So this digit by digit multiplication, this came into place only after this other civilizations could not think of, because they did not have this decimal place value system, or rather place value system. So this decimal place value system was India's contribution, and we can also see combinatorics. Combinatorics was developed in Europe somewhere very late, like somewhere in the 17th century or so, but we were dealing with combinatorics long ago, like in Chandas. Chandas, we will see a lot of combinatorial problems in Chandas, and using that logic, in fact, we can venture a lot into computer programming and stuff like that. Next is solution to linear and quadratic indeterminate equations. So solution to linear indeterminate equation. Linear indeterminate is something like linear, that means it is of first degree, and indeterminate means the solutions cannot be determined, means if you have something like 2x plus 3y equals 8 and 4x minus y equals, say for example, 5. So if we have an equation like this, when we have two equations, we can solve and get the solution for two variables. But if we have only one equation, then how can we get possible solutions for x and y? So if x is 1, this will be 2 plus 3y equals 8. So this will be 3y equals 6. So y equals 2. But that is when x equals 1. But what if x equals 2? So then the whole thing would change. This would be 2 times 2, which is 4. 4 plus 3y equals 8. So 3y equals 8 minus 4. So 3y equals 4 and y equals 4 by 3. So what if x has another value? So like that we can have infinite number of solutions from one equation with two variables if we have only just one equation. So if one equation is given and there are two variables, then the solution is indeterminate because there can be infinite number of possible solutions. So how do we find solutions for such kind of, or how many possible solutions, or like how do you generate solutions like that? Those kind of problems were discussed by Aryabhatta in the 5th century and of course by later mathematicians. And when we talk about quadratic, means it would be of order 2. So some equations like that where you have only one equation and which is of the order 2, then it's called the quadratic indeterminate equation. And negative integers. So negative integers, in fact, we find it like as teachers, you also might be finding this thing when you start teaching negative numbers in school. So children find it very difficult to think of negative numbers, conceive of negative numbers, understand the properties of negative numbers. But this was a challenge faced by mathematicians also till a great time. Except mathematicians in India, they were very famous, like Brahmagupta, he gives rules for operations for negative numbers. But in the West, it was considered till very recent times, till a few centuries ago. So these are two quotations by, not quotations, statements by some famous mathematicians at those times. So 18th century mathematician is saying, concluded that negative numbers are nonsensical. It does not make any sense at all. There is another quotation where it was a common practice to ignore any negative results derived from equations on the assumption that they were meaningless. So these were the kind of views they had at that particular point of time. So negative numbers came much later in Europe, but we were much advanced in those times as well, like in the time of Brahmagupta as well. So these are a few significant discoveries by Indian mathematicians. And if we just look at like the history of mathematics in India, so we can date back to mathematics in the Vedic period, that is the first thing. And second thing, we can say mathematics in the Shulva Sutras. And third one, mathematics by ancient Indian mathematicians. And fourth part, we can say the most recent one, the Vedic mathematics, the book written by Swami Bharati Krishna Tirtha. So today everybody knows what is Vedic mathematics, or at least they have heard of what is Vedic mathematics. But the earlier three parts, most of them are not aware of. So we can see this as the flow of mathematics, or the development of mathematics in India right from the Vedic period. So a few topics that were covered in some texts like Taittiriya Samhita and all. Okay, now when we talk about Vedangas, 6 Vedangas. So just before the session also we were just discussing about this particular thing. So apparently it seems that only Jyotisham would contain mathematics, because we see directly, okay, astronomy, there has to be mathematics in that. But what about other Vedangas like Shiksha or Kalpam or Vyakaranam, Chandas, Niruktam, and of course Jyotisham is there. But if you take, I don't know about Shiksha and Niruktam, so that is why I have not highlighted that. But at least in Kalpam, Vyakaranam, Chandas, there is a lot of mathematics in it. Now one might think, where is mathematics in grammar or like Sanskrit grammar? But last year I had attended one session in IIT Madras, and there they were talking about Panini grammar. So there was one session about mathematics in Panini's grammar. So what they were saying is Sanskrit grammar has got a mathematical nature, a kind of so every sutra if we have to follow, we just have to follow an iterative process, recursive formula. So that particular thing gives a very strong thing, and then you can encapsulate an entire formula into one particular sutra. A small sutra, you just start and then it becomes. So that particular nature. So whatever we take in mathematics, if you want to do a division process, say 31 divided by 7, how do we divide? It is the same procedure for 3, 1, 4, 8, 6 divided by 7. So it's the same procedure that we have to keep repeating. Just keep repeating that procedure, recurring procedure, recursive procedure. So that is the same thing that we do in grammar also. So that is actually the mathematical nature that we can see in Panini's grammar. Okay, so we don't have the power for some time. And okay, and then we talk about Chandas. Chandas sir was talking about a few things in Chandas in the morning. And in Chandas we see a lot of combinatorial and problems on permutations. So how you can generate a lot of things. Say the problem in Chandas was, if you have to make a verse. So those who are not from a non-Sanskrit background, so I'm just going a bit simple. There are two types of syllables. One is Laghu and Guru. So Laghu is the short syllable, Guru is the long syllable. So if I write just Ga, it is like it's a short syllable because there is no vowel attached to it. But if you attach a vowel to it, it becomes a long syllable. And there are some other rules also, that if you do this, then it becomes a long syllable, or if it is followed by this particular thing, it becomes a short syllable. But basically, any syllable or any alphabet can be put under Laghu or Guru. So for constructing a verse in Chandas, if you have to construct a poetic, of course, why we are talking about Chandas is because in those days they were writing everything in poetical form. So in verse form. So how do you construct a particular verse? There should be some particular rule. So if we have to sing a song, if it has to get a melody, then it has to come under a particular raga. Then it gets a very good melody. Otherwise, it is just some particular mix of words and things like that. So for verses also there was a strict form like that. Say suppose one verse can contain 1, 2, 3, 4, 5, 6 syllables. 6 syllables, that is a rule. Say for example. So it can be a guru, 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 guru. Everything can be guru. Or everything 5 gurus and 1 laghu. That can be another form. Or it can be say guru, guru, guru here, laghu here and guru here. Guru, guru. So here this can be another form. So with 1 laghu and rest gurus. So but that also the position of the laghu syllable would change. What if there are 2 laghus? What if there are 3 laghus? How many possible forms are there? So given a 6 syllable prastara, how many possible forms are there to construct? So what should be the formula if we have to list out all the possible combinations? How can we list out all the possible combinations? So there has to be a particular formula. So they were discussing these kind of things in Chandas also. And later on for like the Vedic Chandas, the rules are very different from the kind of meters that was followed in regional languages. So there, if you put, say suppose you put this as the value of G as 2, suppose the value of Guru as 2, Laghu as 1. So if we have to construct a matra with total 6, so it can be Guru, Guru, Guru. This can be one possible way, or it can be Laghu, Laghu, Guru, Guru. So 2 plus 2 plus 1 plus 1. So it can be this possible way. It can be like this also with 2 Laghus. So like that, how many possible ways are there? So to discuss all these things, they were using combinatories. So in combinatorics also we find a lot of mathematical things coming up over there. And then of course Jyotisham is full of astronomy, so astronomy has to have mathematics in that. And then we have Kalpam. So in Kalpam actually they were discussing a few points. Like Kalpam was mainly broken into 3 particular parts. So Rashi Vidya, Jyotisham, one second. Yeah, Kalpam was broken into 4 parts. One is Grihya Sutras, Dharma Sutras, there was another one Shulva Sutras and Shrauta Sutras. So these were 4 different sections of Kalpam. So in Kalpam what they were dealing with rituals, daily rituals what one has to perform for doing the pujas and all. So for doing that, when you have to do a yaga or a homa or a havan, then one has to construct a sacrificial altar. So one has to construct a homa kunda, it has to be in some geometrical shape. So how do you construct that particular geometrical shape? So if it is a square or a circle or maybe a hexagonal shape, so there would be an area specified. Say for example, I am the Yajaman. So in proportion to my height, the homa kunda has to be constructed. So there is an involvement of ratio and proportion over there. And this many times of my height should be the homa kunda in a hexagonal shape. So if you convert that hexagonal shape homa kunda into a circular shape, how can you construct a hexagon in the same area or approximately the same area of a circle? So how do you do this conversion of one shape to another without changing the area? So those kind of problems were like everyday problems faced by them. So Kalpam had one particular part called Shulva Sutras, which were textbooks on geometry mainly, which dealt with constructions, geometrical constructions. So as we can see here, these were some areas where which gave a need for discovery of something new in mathematics in India. So all Indian mathematicians, we can say they were applied mathematicians more. There was a practical need in the society because of which they discovered something new. So geometry came out of that particular thing. And Shulva Sutras, it is usually dated somewhere between the 1000 BCE and 200 BCE. 1000 to 200 BCE. That is a rough dating of different Shulva Sutras. And there were many Shulva Sutras written by different authors. Like one famous one, the oldest one is said to be Goladhyaya Shulva Sutra, written by the mathematician Goladhyaya. And there was Apastamba Shulva Sutra, Katyayana Shulva Sutra. So these were textbooks on geometry. And of course Jyotisham, it contained Ganitam. So this is something that really, this is something that we should learn, especially from those people, because they were doing mathematics not for the sake of doing mathematics. Their objective of using mathematics was a means to an end. It was not just to do mathematics. You have got nothing else to do, so you sit and do mathematics. Not like that. You do mathematics to achieve some particular purpose. You want to calculate the planetary motions. For that you need a tool. So maths was used as a tool to do mathematics over there. Unlike how we learn. So today many find mathematics challenging because we don't know why we are learning this particular thing. We are just learning. So the objective of learning has become totally different now than the objective that was at that particular time. So whatever maths they were learning, in those times it was very meaningful to them because they knew why we are doing this. Why I should learn this particular thing, because it is applied over here. So for the same reason there was no separate text called Ganitam. So Ganitam was something that one is taught while he is learning Jyotisham and other areas. So this is where we can see mathematics in Jyotisham and Kalpam, and these are a few in Shulva Sutras. And okay, these are a few topics I am just roughly going through just to give a feel of what kind of topics were discussed in Goladhyaya Shulva Sutra. So Shulva has got one meaning. Some say Shulva is like it's the name of a leaf. Many say that it's Shulva means to measure. So to measure what was used, rope was used. So again another meaning for rope they say is Shulva. Do you call Shulva for a rope in Sanskrit? Shulva is to measure, that we use, right? So the mathematics for measure, sorry?
It's an easy way. Sulabha means?
No, that is another interpretation. Sulabha is different. This is Shulva. There is Sulabha.
I read it some particular person's name. Shulva Sutra and Apastamba Sutra.
Apastamba is named after Apastamba. Goladhyaya is named after. So Goladhyaya's Shulva Sutra is Goladhyaya Shulva Sutra. Apastamba's Shulva Sutra is Apastamba Shulva Sutra. So a sutra used a textbook used for measurements. So since they were geometrical texts used for doing geometrical constructions and mensuration, it was the name Shulba is derived, and these were the topics that were dealt in the Shulba Sutras. And if some of you might have witnessed some yaga, I'm sure like most of you might have, but in many yagas you will find geometrical shapes, altars of these geometrical shapes, where you have to construct a square which is of the area of a semicircle. So it will be approximately the same, but how do you construct a particular, how do you interchange shapes? Or if you have to construct say a hexagonal altar or an altar of trapezium, so how do you construct a square altar and a trapezium altar without changing the area? So those kind of topics were discussed in Shulba Sutra, and the Bhujakoti Karna Nyaya, the so-called Pythagoras theorem, that was discussed in Baudhayana Shulba Sutras 3-4 centuries before Pythagoras. So these again, in Shulba Sutra we can also see this Pythagorean triplets that we learned, and this approximation of root 2 and all those topics were also discussed. And these are a few names of few mathematicians for those who are not from a traditional Sanskrit background. I'm sure those who are from there, you must have heard many of these names. But Aryabhatta, Bhaskara, Brahmagupta are a few names that we have seen. But there were many mathematicians at different time periods. In fact, there was a separate school of mathematics in Kerala itself, which recently has got, people are discussing on that. So this, it's not very neat because the list is very big. So it starts from Madhava, that is 14th century, and from there his disciples up to the 19th century we can see the lineage of mathematicians, and these are just Kerala mathematicians. So these are again a few topics covered in Aryabhatta. Aryabhatta is the text that we can say after Shulba Sutra period. Shulba Sutra was the BC period. So most significant text immediately after the BC period we come across is Aryabhatta, which is in the 5th century. So Aryabhatta itself, we can see what all topics we learn in school today. So all those topics are covered over there in Aryabhatta and much more. So and of course Aryabhatta's this was a very significant thing that he said, that the value of pi. He said it is not just 3.1416, he uses this word approximate. He says that this value is approximate. So how did he arrive at this particular value of pi? So for that also different scholars give different interpretations. He would have known that it is an irrational number, and then he devised a logic. But then for practical purposes up to 4 decimal places is more than enough. So that's why he probably stopped at 4 decimal places. There are a few more topics. Solutions to linear and indeterminate equations. Again, it's really interesting. At 5th century, they were discussing these topics. Again, a few topics from Brahmaspura Siddhanta. So, just maybe a century later is the time of Brahmagupta. Again, this Varga Prakriti is what sir was talking about, quadratic indeterminate equations of order 2. So that was discussed by Brahmagupta, and then he gave a principle called Bhavana principle, which was much refined later, and then Bhaskara gave a principle called Chakravalam. Using that particular thing, you can solve, it's another way of solving quadratic indeterminate equations. So this was just something I just wanted to touch upon before we start on Lilavati as such, because those who are totally not from Sanskrit background, at least, so that we can get a picture like how mathematics was developed in India right from the Vedic period. Okay, so this is an interesting picture which I found on the internet. Yes?
We can keep machine there, I can help you for this.
No, it's okay. Thanks.
Yes, right, this one.
Okay. As we all know, this year is the 900th birth anniversary of Bhaskaracharya. So one thing that we have to really be, one should think is how did a textbook written by Bhaskaracharya in the 12th century is still used as a textbook for Sanskrit medium courses. So what kind of beauty would it have? I mean, this was the first thing that anybody would think of, and about Lilavati. So Lilavati forms one of the 4 portions of a major text that Bhaskara had written in 1150 CE, Common Era. So Bhaskaracharya was a famous astronomer, a great mathematician, and a wonderful teacher. So wonderful teacher, we can see from the text, the quality of text that he has written. So one has to be a good teacher to write such things. And then he wrote 4 major works, like 4 major things that comes under Siddhanta Siromani. So first is Lilavati. Lilavati basically it comes under this category called Patiganitam. So Patiganitam is usually used for arithmetic, but he does not just deal with arithmetical operations. He deals with many other topics also in this particular, even some rules on trigonometry also in Lilavati. So he calls this as a Patiganitam text, and second text that he says under Siddhanta Siromani is Bijaganita. So Bijaganitam is a text that deals with algebra in great detail, and in Sanskrit medium courses for higher level classes for mathematics, they discuss Bijaganitam also. And then comes 2 other topics, which is Goladhyaya and Grahaganitam. So these 2 topics, Goladhyaya deals with spherics, and Grahaganitam it deals with planetary motions, planetary mathematics. So combined these 4 comes under Siddhanta Siromani. That is what is generally said. So Siddhanta Siromani is a bigger work, and it is under this particular, like in Goladhyaya he writes this dating, that on this date of Shaka era I complete this particular work. So this 1150 AD has been derived from the dating given in Goladhyaya. So it is said that he completed the whole work in 1150 AD, and he is believed to be from Karnataka or from Maharashtra. So different scholars have different opinions about the location, because the names of the place, everything has changed. And among his many commentators, there was this commentator called Ganesha Devajna, and his commentary Buddhi Vilasini, which is one of the most famous commentaries, and in that he says that Bhaskara is Ganaka Chakra Chudamani, the crest among all mathematicians, crest jewel among.
Buddhi Vilasini is what?
It's a commentary for Lilavati. Sorry, Ganesha Devajna commentary.
Buddhi Vilasini.
Is it available, sir?
Yes, it is available. So it means here.
No, yeah.
It's available in print, you are asking. Yes, it is available.
From which publication?
That will check with Heroor. So all those commentaries, publications and all those things, all those lists can be available. And he was associated with the Ujjain school, and these are a few works. Okay, the 14th chapter of Goladhyaya, that comes, that is called Jyotpati or Jya Utpatti. So that is like a small tract of birth of trigonometry, or like how trigonometry was used in India. So this Jyotpati, in fact Heroor sir has written a book called Jyotpati. It's a very small book, and it explains about the Hindu trigonometry in those days. So Jyotpati was one chapter of Goladhyaya, and of course Vasana Bhashya is Bhaskara's commentary on his texts. So why is the need for a commentary? Because the texts are usually very precise, they just come in verse forms. So maybe he will, the authors would just give an example, 1 or 2 examples explaining the text, and it's up to the commentators to explain it more. So it is not like our today's textbooks where we find a lot of explanations. But in those days textbooks were maybe like in a tablet form, and then commentators provide more and more explanation to that. And we often find commentaries of commentaries. Like there is some original text, there is a commentary written on that, there is a commentary written on that particular commentary, sometimes even a commentary on that particular commentary as well. So even then we find it very difficult to understand. So, without commentary, I really wonder how the people they would understand these texts. Okay. And Karana Kutuhala is another text, and commentary on Lalacharya. Lalacharya was another mathematician, and on his text also. So these are a few texts that Bhaskara had, Bhaskara II. So we call him Bhaskara II because there was a mathematician Bhaskara I before Bhaskara II, and that's why to differentiate between the two is called Bhaskara II. Okay. So roughly it comprises of 278 verses. Now this number of verses in different texts and different commentaries, it would change. Some verses are missing, or sometimes maybe one and a half verses would be considered as one verse in one particular text, and another particular text it would be considered as two different verses. So the verse numbering would change. So I suppose you all have got one printout of the verse form of Lilavati. So what Heroor sir has done is, he has done 3 different sections. Like if you take Ulbrook's Lilavati, verse number 72, and if you take some other publications Lilavati, there it would be verse number 70. So if you just look at the meaning, then you will say, hey, 72 verse meaning and 70 verse meaning is different. But then the verse would be, numbering would be different. So he has given an indexing for numbering for different things. So that printout we will give tomorrow. So with that we can keep text in parallel, and we can try to look at the text. And these are a few topics covered: 8 basic rules of operations: addition, subtraction, multiplication, division, squaring, square root, cubing, cube root, fractions, and rule of 3. Rule of 3 is nothing but the rule of proportion. If x things, if 5 things cost 10 rupees, so how much would 20 things cost? So 3 things are given. To find the fourth particular thing is called the rule of 3. 3 things are given. So basically we do it by cross multiplication, the thing that we learn in school. But we just don't hear this word rule of 3 as such. Okay. And interest allocations, there are few problems on mixtures also, and problems producing simple and quadratic equations, arithmetic and geometrical progressions, permutations, combinations, indeterminate equations to the first degree. Properties of triangles and quadrilaterals, again an interesting topic. Areas of circles, volume, shadow problems, and last is Kuttaka. So these are the topics in short covered in Lilavati. But Bhaskara does not give an index as such. He does not say that okay, chapter number 1, chapter number 2. It goes in a flow. But commentators like the main commentary that I have followed for making the presentations is H.T. Coolbrook. So Coolbrook's commentary is one of the most authentic commentaries, and that particular text I have followed. In that he has made some indexing that is for our understanding, our easy understanding. And these are a few famous commentaries, and out of these the most famous commentaries are Ganesha Devatnya's Buddhivilasini, and there is another commentary called Kriya Kramakari, written by Shankaravarya, another Kerala mathematician. So these two are said to be the best available commentaries on Lilavati, and of course there are a few more commentaries. And these are all commentaries in Sanskrit, but we can see a lot of commentaries of this particular text in regional languages also. So Lilavati is probably the most translated, or the text which has the maximum number of commentaries. And the same author's other text did not become that popular. I mean, they were of course considered very important. Like Bijaganita, for example, it deals with higher level mathematics. So then, for ordinary people, there would be maximum crowd for ordinary mathematics. But when you go to specialization or for higher level mathematics, the number of people who are interested in that would be lesser. So probably that can be some reasons why the other text did not get that many, viewership or spread or that much commentary. But Lilavati, since it starts with arithmetic, everybody has to start with arithmetic. Everybody has to do mensuration. So while we are learning any course, so all these topics are useful for people of any age. So that is why probably Lilavati got so much of publicity. I mean, it became very popular. popularity, I should say. And it was, there are 3 Persian translations known, and one translation is Tarjama-e-Lilavati by Abu al-Faidi. In fact, this story of Lilavati is a bit popular thing, that Bhaskaracharya had a daughter. Her name was Lilavati. So he named the text after the daughter's name. So this is a story that comes in the Persian translation. Bhaskara does not say in Lilavati that I had a daughter I named, or neither does he say in the commentary. But in the Persian commentary, this story somehow comes up. So we can't say how far this particular story is true. But I mean, for the sake of those who have not heard this story, I'll just share it. It goes like this. So Bhaskara has a daughter, and her horoscope says that she has to be married in one particular muhurta. So if she is not married in that particular muhurta, then her marriage either will not happen, or it will be a disaster, or she has to get married in that particular muhurta. So Bhaskara devises a very good water clock. So what he does is he makes in a vessel, he keeps some water. So this is a vessel and it's filled up with water, and there is another vessel kept on top, and there is a small hole here. So the time taken for the vessel to get completely immersed will determine, at that particular muhurta, the vessel will get completely immersed. So this is like our sand clock. This he made a water clock especially for that particular purpose. So it is said that Lilavati, when she was a little girl, so she got curious and she was looking into it. So a pearl fell from her nose ring into this particular thing, and it got stuck here. And after some time also Bhaskara is thinking why this particular thing is not going down, and then he checks, then he finds that okay, the pearl is stuck in that particular space, and that is why it didn't get immersed. But by that time, the time has already elapsed. So the story goes like the daughter, either she got married and then the marriage was a disaster, or she never got married. What happened, we don't know. But then to please her, to make her happy, he writes this book. So that is why in the book, many places we find these verses. Oh beautiful I Lilavati, oh dear Lilavati, my dear Lilavati, if you are really smart enough. So all those kinds, this is how he is addressing every question. So at every question you would say, oh dear Lilavati, if you are smart enough, can you tell me the answer of this particular question very quickly. So it is said that he uses, that is why he uses these kind of wordings to please his daughter. So but the authenticity of this story cannot be checked as such. Okay. So again, in many other regional languages, it has been translated, and of course, English translation H.T. Colebrooke's is one of the famous translation and very authentic. So there are many special features in that, but here we find the first time somebody is talking of division by zero. Even though before that mathematicians were talking about zero and operations like multiplication, division and all, nobody has specifically said about division by zero. So it is here that we find, and he uses this term kha hara. Hara means to divide, kha is used for representing zero. So kha means akasha. So there are 3 ways of representing numbers that was used in ancient India. So one was used by Aryabhatta, and it is called Aryabhatiya number system, and it was used by Aryabhatta only. Nobody else dared to use that particular way of writing numbers because it was very complicated, and that was one particular system. Another system was Katapayadi number system, so where every letter is given a number. So if you are writing a name, say like not V-I-N-A-Y, Vinay, Va, Na and Ya. So then Va, Na and Ya can represent 3 letters. So that goes for Katapayadi number system. And Bhuta Sankhya is something different. So Bhuta Sankhya means you use objects to represent numbers. So objects like if you want to use 3, so maybe you will use Tretagni. So Agni is 3. So Agni, if you see the word Agni, it represents the number 3. You see the word Danta. Danta means teeth. So there are 32 teeth. So Danta means 32. So like that. So Shashi or moon, it represents 1 because there is only one moon. So like that. So for every, of course, there will be one has to be very well versed with Indian Puranic text also, because many things appear from those areas also. So that comes under Bhuta Sankhya. So Aryabhatiya number system, Katapyadi number system, Bhuta Sankhya number system, where the three number systems used, and this Tha in Thahara, Tha is used for representing space. So it's a synonym for space. Tha means space. Thumb. So thumb means space. So space is the thing used for 0, representing 0. So Thahara means division by 0. So and he just mentions that, and in Bijaganita he says that okay, division by 0 is infinity. In Lilavati he does not say much anything about that. And the last topic of last chapter of Lilavati deals with very little complicated problems on combinatorics. And another topic that he discusses is Bhujakoti Karna Nyaya, and he gives a proof for a proof which is geometric as well as he gives a geometric as well as algebraic proof for Bhujakoti Karna Nyaya, that is Pythagoras theorem. And both these proofs, geometric as well as algebraic, it appears very late in Europe. So that was discovered much earlier in India. There's another quote since it's not here. So this is a quote by Professor Coolbrook. So he says, had an earlier translation of Hindu mathematical treatises been made and given to the public, especially in the early mathematicians of Europe, the progress of mathematics would have been much more rapid, since algebraic symbolism would have reached its perfection long before the days of Descartes, that's a mathematician of 16th century, late 16th century, and Pascal and Newton. So Goldberg feels that this kind of beautiful mathematics we were dealing at that point of time. So if that would have reached Europe earlier, so then mathematics would have progressed a lot faster. So this is in short about Lilavati and the topics and the commentaries and all that. Okay. Now we'll just directly go to. Okay, if you want to ask something or any specific comments in this, we'll look at that, and then we'll go to the text as such.
I have something to add.
Yeah, please.
I hope you don't mind.
No.
Every time I'm saying I have something.
No.
One thing is in the Chanda Shastra, I have not read the Sanskrit text as such, but I believe not only the discussion on combinatorics, but they also have a formula to get to an appealing chandas. Out of that, they created verse meters.
Okay.
So this is something interesting for the modern day computer science. See, like what we do in modern day science is, suppose morning sir was also talking about that in music and all these things, they do follow mathematics, even language.
Correct.
We can have so many constructions in languages, or we can have so many types of constructions in musical notes and all. But that are appealing are prevail. So that means the appealing also has been quantized there.
Okay.
So the quantification of that has also been discussed there, maybe implicitly, but I believe that is there.
Okay.
Because of that only they say that Yamatara Jamal. More than that, I had come across a paper by a Polish scientist, linguistics actually. What he has done, his research was on one chapter of Mahabharata epic, and there, even though we say, okay, Anushtupa Chanda means this thing, but in that also, not say for example, Guru, that doesn't always mean it could be E, U, or something like that, and therefore that homonymity is there. One Guru can be represented by many other vowels.
That is there.
Yeah, therefore it creates lot of combinatorics. in our language combinatorial explosion it may arise, and then out of that what are interesting combinations, those are prevail. So his research was showing the computational analysis of what are prevail. For example, word Rajan and Radnya, why should you not use Rajan and Radnya is used many times, or other way around, I may forget such thing, but then he gave that proof, or why one thing is, one thing comes with more weight than the other, that is following Chanda Shastra.
Okay.
That was very interesting. I have not seen Indian researchers doing such kind of research, but yes, foreigners have done a lot on that.
In fact, Heroor sir has written a book on combinatorics itself, on the Chanda's combinatorics. A separate book altogether. Okay. Yes. Yes.
This also.
Yeah, this one. What's the development of combinatorics from Chandas, right? Satyayas and Sanskrit.
And that is another thing is, that was part of my thesis. When I wrote something on contemporary relevance of Katapayadi, everybody asked me to write genesis of Katapayadi, which really does, nobody knows actually. Here and there we get references.
Who is the author of Katapayadi is not known.
Who invented the system. And that's not new to us as far as Indian tradition is concerned. But yes, to make the thesis complete, I had to study a lot, and then I got to one of my speculations is that why this kind of number system would generate. Maybe in the initial stage, that much before Apastama Sutra and all, in Vedic Kal, the people were studying the nature, and some of them could arrive to certain conclusions. Then they wanted to pass on the messages to the other part, and if we can see the demographic areas over what it has been spread, the kind of things, the kind of rituals and all. And then that was one type of scientific formulation. That was a need to formulate it scientifically instead of literature form. Sutras first come out of that. Later on, they wanted to make it more formal. In that we can see in Apastamba Sutra as well, like in altars, where should somebody, Yajman should sit, and so that the smoke will not disturb him, and that kind of gestures and assumptions are made over there. So considering the environment, how mathematically you can formulate the nature or any given situation. Now, it's very difficult to formulate even a mathematical problem, but much more than that, it is difficult to formulate the non-mathematical problem. So many other constraints. So there was an attempt to make that in Apastamba and all. Later on, they made sutras out of that, and those sutras, we treat them as a geometrical formula. That you were telling conversion of this form to that, the shape conversion cycle. Later on, Jyotish, they reached much beyond that. They started studying celestial entities and all. There was need of numeric figures of long integers or whatever, long sequences. And then by following the golden rule of 7, it was very difficult to expect somebody to remember that long integer, and therefore there arose a need of having something what is called as mnemonic.
Right.
And therefore that Buddha
I think we can have a totally different discussion on this particular thing, because it will be a very good thing if we can sit and discuss. For the session thing, I'll just excuse me. So this is the invocatory verse. I am not going into the details of the invocatory verse. So it's mainly it's praying to Lord Ganesha that let this verse go very well and let it. So we'll just read it since we are also starting. So having vowed to the deity whose head is like an elephant's, whose feet are adored by the gods, who when called to mind relieves his votaries from embarrassment and bestows happiness on his worshippers, and propound this easy process of computation, delightful by its elegance, perspicuous with words concise, soft and correct, pleasing to the learned. So this is the invocatory verse. So in your printout, you will find this as verse 1. So I am just putting this verse 1 on the top, and here this is verse 2. So these are terminologies related to money transaction. So in those days, as we all know, money was there were different things used for trading and also cowrie or kavadis that we call them. So 20 cowries is 1 kakini and 4 kakinis is 1 pana, 16 pana is 1 drama, 16 drama is 1 nishka. So nishka, you will find this dot below S. So the second sloka, verse 6. So this is pronounced as Sha, Nishka. And if a dot is put or a small line is put above S, it is called Sha, like Sharada, Sha. So just those who are not familiar with the diacritical marks, so this is in verse 2, and verse 3 is mainly it deals with the weights. So 1 gunja is 2 barley corns. So even that small particular thing they were weighing. So it's not just grams. They are not starting from they are going very to small measurements as well. So 1 valla equals 3 gunja, 1 dharana is 8 vallas, 1 it is Ataka, right? In the printout, this might be as Ataka.
Sir, hopefully we shall read first Sanskrit words. Most of them are lost otherwise. We will start with English.
I thought we will go more into the mathematical part, since these are just terminologies. Or if you want to look at the terminologies, then we can look at the Sanskrit words and however you want to do. Otherwise, if you want to look at more on the mathematical part, then we can go. So that's why I was just running through the terminologies. What do you feel? You want to go word by word for terminologies? Then we can go. Okay. So these are just some terminologies. So
reading the words and then going through the terminology will work.
Okay. So this is verse number 2.
Since they will understand in Sanskrit, our purpose is served, and then other people can understand in English.
So Varatakanam Dashaka Dvayam. So Dashaka Dvayam. So Dashaka means 10. Dvayam 2. So Dashaka Dvayam is 20. And Yatsa Kakini. So again that is 1 Kakini. And Tascha Panascha
That will be better. Na Sanskrit people let them
yes, okay.
first words.
So if you can just read the first word, just read, somebody just read it loud. Means Varatakana.
Varatakanam dashakadvayam yat sakakini tascha panaschatasraha te shodasha dhamma vibhavagamyo dhamaistatva shodasha dishta nishkaha.
Okay. So I'll just refer to the mathematical terminologies here, like Dashaka is 10, Dvayam is 2, so 20, 2 times 10, and Sa Kakini, so that is 1 Kakini, and Chatasraha.
4 multiples of kakini.
That is 4 times 4. And Shodasha is again 16. And Drama, so
this will also serve the time, sir. They know English, so they only will translate by reading Sanskrit.
Shodasha again, that is 16. So basically, if we just go word by word, we can just look at these numbers and then we can understand what is that. And with this, what is Kauri and all that, it is given in the Coolbrook's translation. So we will give you a soft copy of the Coolbrook's translation, whoever wants that. So the English meanings, word by word meaning, whatever you require. Not word by word, the meaning of the verse that we'll get from that. Okay. I think words by words we can go. These are just terminologies, so these are,
that aesthetic is not in English, sir.
So these are, we'll just look at the terminologies and then we'll go ahead with the mathematical part more. So again, verse 3 and 4, they deal with weights. We can see as small as 2 barley corns, and then it goes times, and then finally 1 karsha of gold is called 1 suvarna. And in verse 5 and 6, they discuss 8 breadths of yava. So yava was barley corn. So 8 breadths of yava is 1 angula. So angula is finger, and 24 angula is 1 hasta. Hasta is hand. 4 hasta, 1 danda. 1 krosha equals 2000 danda. 1 yojana equals 4 krosha. And this terminology of yojana, I feel it is different in different time periods, right? In different texts and all, like if you talk about Pauranic texts,
Maybe
that's
very near to kilometer.
But again, if you talk about Mahabharata, Ramayana and all, the distance of yojana is different in different texts. So this is the distance that was discussed at that particular time.
In angula also there is 3 types of angula. So in 6 breadths of yava is adama angula.
Okay.
And in 7 breadths of yava is madhyama angula.
That would be in different time periods.
No. In Ganita Tilaka he is also telling. Sripati also. Same period. It means Uttama is
Different places probably. Different kingdoms.
not like that. Uttama is considered always good.
Okay.
So other also
Like how we have a gallon. A gallon in US is different from a gallon in UK. The quantity is different. Same like dollars, Singapore dollars, US dollars. Dollars is the same, but the value is different.
it means some of the area. In Yava, in Madhya Pradesh it will be bigger.
One.
And in other area it will be smaller.
Probably, yes.
Because of that,
The size of the barley corn would be different.
Yes.
So these are a few measurements again. Okay, and yes, measurements of time he has not discussed in Lilavati. He discusses that in the other part of Siddhanta Siromani, some other, like Lilavati is the first part. I think he discusses maybe in Grahaganita, planetary motions. Siddhanta Siromani. But Lilavati itself forms a part of Siddhanta Siromani. There are two views in that. Some say that only Grahaganita and Goladhyaya will come under Siddhanta Siromani. Some say Lilavati, Bijaganita, they are also a part of Siddhanta Siromani. But this he deals with, I think in Grahaganita, planetary motion. There he will have to talk about time. So there he discusses about time. Here he does not mention about time. Okay. So then we start with arithmetic. So again there is an invocatory words, and then he starts with powers of 10. So starting with the place value system, ekam chame dasham, so eka dasha shata, and then he goes to up to 10 raised to 17. If you look at the verse number 10 and 11 in the printout, you see all these terminologies are powers of 10. So 10 raised to 7. Today I just googled 10 raised to 17. What it means, like what do you call such a big number? So it is 100 quadrillion. 10 raised to 17. So 10 raised to 17 is today called 100 quadrillion. Okay. Then verse 12 he explains the rule for addition and subtraction, and 13th verse is an example for addition and subtraction. So till here I am just running, and then we'll look at terminologies, and then from multiplication we'll go into a little more detail. So Anka is the word in the words we can see in many places. Anka signifies represents a digit. Shunya would represent 0. Anka and Sankhya. So Sankhya would represent a number. Anka would represent a digit. So okay. So 8 basic operations for that parikramashtaka. So 8 basic operations, which is addition, subtraction, multiplication, division, and square root, cube root. Sankalana, Sankalita, Mishrana, Yuti, Yoga, all these are some words used for addition or summation. So whenever we come across such words, it means okay, Sankalana. Sankalana is Sankalana or Sankalita. That we will find in series also, arithmetic progressions or summation of summation, like sum of all natural numbers, sum of triangular numbers, all that. We'll come across these words Sankalana and Sankalita. Vyavakalana is the opposite, subtraction. Vyavakalana, Vyavakalita, Shodhana, Patana, and those are for subtraction. Antara is the difference. And okay. So in the verse 14 and 15 he explains 6 different rules for multiplication, and he uses 2 terminology like Gunya and Ganaka. Today in modern mathematics, at least we have not learned this multiplicand and multiplier in school. I think it was there earlier. You were using something like that, 12 multiplied by 44. 12 would be called the multiplicand and 44 is called multiplier, because with 44 you are multiplying. Either ways also it doesn't make any difference to mathematics, but for terminologies they were using that. So Ghata means product. So to do 135 and 12, the procedure. So this is one particular procedure that he uses. So what he does is, as we can see, 12 times the units place digit. So that we have to do, and we have to write 60. And then we have to do 12 times the tens place digit, 36. But we have to arrange that in a slightly different way. We will not write below 60, we will just leave one space here and write here. Just like how we do multiplication and then the second step we add. So we leave one space. And third is 12 multiplied by the hundreds place digit. So again you leave a space here, you write 12 and then you add. So you get the answer of 135 multiplied by 12. So this is called Tatstha method. It was discussed earlier by other mathematicians also, or their methods was also similar to these kind of methods. So the arrangement would maybe differ. Maybe somebody would say that okay, you write 12 into 1 first and then you write 36 below that in the reverse particular order. So that is also possible. So if somebody wants to do multiplication like this, like 12 multiplied by 1, then 12 multiplied by 3, then 12 into 5, and then you write down in a slanting order like this, and then you add, you will get the answer. So this is one method that we discussed. Or the other way around, like instead of doing 12 into 5, you can do 135 into 1 and 135 into 2. And again, there you can see the slanting order. In that particular order, we write, and then we can get the result. So this is one particular way of multiplying. Can I go ahead? And this is a method given by Ganesha Devakia in his commentary. And sometimes I had seen this somewhere over the internet as how Chinese do mathematics, and they were showing this kind of method. I don't know Chinese if they really followed this particular kind of method, but anyways, this we can see in Ganesha Devakia method. So what he says is, you write 1, 3, 5 and 1, 2 like this, okay, and divide into smaller sections. So every rectangle we are dividing into 2 parts, 2 triangles. So first what we have to do is this 5 multiplied by 1. We write it 5. And then 3 multiplied by 1 is 3. And then 1 multiplied by 1 is 1. Then we go 5 multiplied by 2. So we have 2 digits now. So we write 0 and 1 like this. And then 3 multiplied by 2 will be 6. 1 multiplied by 2 is 2. Now how to add this? Now we have done this. Now the addition procedure is remaining. So we have to add by this slanting lines. So first is here 0. Then you add 5 plus 1 plus 6. So like this we add. So we get 12. So we write 2 here. Slanting. Whatever is coming in this section will be added. And the carried over will be here. So 3 plus 2, 5 plus 1 carry over, 6. And then this is 1. So this might look a bit complicated, but we can just imagine this as I don't know if Heroor sir has brought this. Last time he had brought strips of this. That is, if you how easy it is if you want to do multiplication like this. So suppose you want to multiply 56. You want to write the table of 56. So you take the table of 5 and then you take the table of 6. So 5 ones are 5, 6 ones are 6. 5 twos are 10, 6 twos are 12. Again 5 threes are 15. 6 threes are 18. Again, like that you go on. So if you want to do 56 multiplied by 2, say for example, so you will have to take up this particular line. So 2, let me just rub the remaining part. So this is from the second column, second cell in the column, So 2, 1 plus 0, 1 and then 1. So 56 into 2 will be 1, 1, 2. Or if you want to take a 2-digit number, say we want to do 32 multiplied by 23 or say 24. So again we can write 3, 2. This is 2, 4. First we will do 2 multiplied by 2, 4. 3 multiplied by 2, 6. 2 multiplied by 4, 8. 3 multiplied by 4 is 12. So if I write it like this, so now we have to add, this will be 8. 4 plus 2, 6. 6 plus 1, 7. So 7, 6, 8. We'll try with some carryover numbers. Instead of 2, let us take say 6 here. So first will be 6 multiplied by 2, 12. 3 multiplied by 2, 6. Then 6 multiplied by 4, 24. 3 multiplied by 4, 12. Now we have to just add 4. 2 plus 2 plus 2, 6, 8, 8, 16, 4. So this is how we add, and the more number of digits we have, the more number of columns we have to take, and just follow this particular procedure. So this process was given by Ganesha Devati and his commentary, Buddhivilasini. I hope this method is clear, right? Another way that he says is, an intelligent way of doing this would be splitting the number 12. See if the number 12 can be split as some other way. So here he says we split as 8 and 4. Now why should we split as 8 and 4? Any guesses?
8 is a multiple of 4.
8 is a multiple of 4. So if you know what is 135 multiplied by 4, just double it and we get 135 multiplied by 8. So we have to do one particular operation. So here luckily for us 12 can be split as 8 plus 4, where 8 is 2 times 4. So you just have to do 135 multiplied by 4 and then double it. So 135 multiplied by 4 can be done easily, and then just double it and then add the answers. So this is another way of multiplication that he discusses. So we can even try out for another example. Say suppose I want to do 48 or say 24 multiplied by 15. 24 multiplied by 15. So which number would you like to split?
10, 5.
10 and 5. So 15 can be split as 10 plus 5. So we can do one of these operations really fast. Most of us can do 24 multiplied by 10. So which will be 240. Then 24 multiplied by 5 will obviously be half of the earlier one. So we are not doing 24 into 5, we are just taking half of that, which is an easy procedure. So this will be 360. This is not possible for every numbers. Of course, we have to get numbers which can be split in this ratio, like ratio of 2:1 or 3:1, where we can do calculations really fast.
This is a part of vedic maths.
This, principles are same. Okay, so this is another method that he says, and another method he says is you split 12 as 4 into 3. Earlier we were splitting as 8 plus 4. Now we split this as product of two numbers. So 135 into 4 into 3 is the same as 135 into 12. So what we have to do is we have to just multiply by one particular number. So for some of us it might be 135 into 4 would be easy. So 135, double of that will be 240, double of that would be 270, double of that would be 540. So then take 540 and take 3 times of that. So this is another way that he suggests. So again here we can say 15, instead of splitting as 10 plus 5, we can split this as 5 into 3. So maybe 24 multiplied by 5. I am getting a number ending with 0. So it is easy for me to multiply. And then 120 multiplied by 3. So that will be 360. Or maybe somebody knows 24 into 3 is 72 and then 72 into 5. But then if I do into 5 first, I get a number ending with 0. So then that can be some intelligent way of dealing with calculations. And again into 5, just for the sake of teachers I am saying, when you are going to students and all. So into 5 again, instead of doing multiplication by 5, we can also ask them to think like 10 by 2. Because division by 2 would be easier and then multiplication by 10 would be easier. Okay. So this is another method that Bhaskara suggests. And fourth method is you just split 12 as 1 and 2 and then you add it like how we were adding in the first method. You remember, you just slightly shift the place. So what he is making use of, he is making use of place value system over here basically. 1 and 2. Instead of taking 10 and 2, just write it as 1 and 2 and shift the position little bit. So this will be the same as 135 into 10, 1350. If it is 135 into 10, a 0 would come here and then it will be 1350 plus 270. So he is just trying to avoid those zeros so that the calculation can be little easier. Here if it is 135 into 10, a 0 would come here. Right? And then if you add, it would be same addition. But instead of that, we are just leaving one digit. I mean, here we are leaving a space and we are writing it like this. In the screen, I think because the numbers are little small, some of you from where you are sitting, it might not be very clear. So this 24, let us take 24 into 15. So what he is saying is, I will split 15 as 1 and 5. So I will do 24 into 1. 24. And then I will do 24 into 5, but I will not do 24 into 10. I will do 24 into 1, which is 24. And then I will do 24 into 5. So that will be 120. So 1, 2, 0. I will just leave one space here and I will write. So when I add this becomes 360. So here also I have actually left one space here. One space which is not very clear because the fonts are little small. So just leave that space and then write, so it is taking that. So basically there is not much difference between this method and the first method, but anyways he states this as another method. Okay, and another way is of course splitting 12 as 10 plus 2, the basic thing that we learn in algebra. So just multiply. And the sixth method is reduce it. So this can be used instead of 20 if it is a number like 19. So 20 minus 1 would be easier over here. So like this he explains 6 basic rules for multiplication. And rules for division in verse 17. He is actually explaining long division as well as simplification. So,
sir, which method is very useful in which area?
For multiplication, right?
Yeah.
That one has to decide based on the numbers that we are getting. So, if it is say, let us look at a few examples, then we will see which of these three, what all techniques we have discussed. So, if you are having this 24 into 15, another is 24 into 19, another is say 39 into 12, say for example these three calculations. So this here we can even split this as 10 plus 5 and take into 10, so this will be half of that, that would be one way. Or this can also be done as 1 and 5, adjusting the positions, that is also possible. But when you go to 19, instead of doing 1 and 9, would be little difficult over there. So you split this as 20 minus 1, right? Or Ganesha Devatnyas method, that is also applicable there. And 39 into 12, again here also you can do 40 minus 1, or again think of 39 into 1 and 39 into 2, because it is 1 and 2, so it is not very difficult. So what we can see here is, earlier mathematicians were giving many ways of doing multiplication, and the standard or conventional method that we are learning today in school, that was usually recommended for the dull-witted students, because those who cannot think of splitting numbers like this, because this is the intelligent way of doing, right? I mean, this is how smart people will do. But not everybody can think like that. There would be at least a few students in the class who can't do. But unfortunately, we all follow that particular method only today. We don't learn, I mean, of course we learn this when we go to higher classes, but where do we apply this particular thing? We don't learn it. So that method, I read it somewhere, it was called, the conventional method that we learned, it is called the method for the dull-witted students. And these are the terminologies in division, like bhaga, hara. In Malayalam also harikya means it is division. Haratu means into. That would be, harana means it is division, you divide. Or I don't know how if it is getting a meaning into. Reduce. So, okay. So, bhajya means dividend, bhajaka is divisor, labdhi quotient, sheshaka remainder. What remained? Jo sheshaka, like sir was talking in the morning. Shesha. So, shesha means remainder or sheshaka, labdhi is quotient, bhajaka is divisor, or hara is also called divisor, what you divide, and bhajya is dividend. So, these are harana, chedana, so these are some other words used for division. I think we'll take a break. We'll continue with the division procedure in the next session. Let me just check. Division procedure. Okay, division procedure is nothing but the same long division method that we learned today in school. So that is why I have not written that division procedure over there. So if we have to divide 1, 2, 3, 4 divided by say 11. So how do you divide? So take the first. So this particular procedure that we are using today, this was the same procedure that was used earlier. Or rather, this is the same procedure that has been carried on. And another procedure that he gives is simplification. So if you can actually simplify, it is 1, 2, 3, 4 divided by 12. So the moment you say, okay, it is an even number, so divisible. So again we can simplify. So simplification method. So here, instead of doing long division, we can just simplify and get the answer over here. So these are the two methods in division that we suggest. And for squaring, square root and all, it is little different from what. Basically, the technique is the same, but the modus operandi is little different. So we will learn. We'll look at squaring later in the next session. So I think we'll take a pause here before it starts pouring down heavily. We'll quickly go have it with us. Any comments in specific? Taking the rings into consideration. Sorry. Only this because for multiplication we have many options, but for divisions we don't have that many options. We'll take a pause here. Yes sir.
So Bhaskaracharya have given only problems. He didn't solve any problem.
Correct.
This particular thing.
Yes, if we have to mention. Correct. All
it is very important because he have not given any solution.
Correct. He just in the this thing also he mentions this is the answer. This is the quotient. This is the remainder. But how do you particularly do this? If you look at the multiplication verses, look at this verse number 14 and 15. In that he explains like how you have to divide. So that explanation is there. But this form of explanation it is not there. But in the verse form it is given. The explanation is given.
He first discusses the method and then poses a problem. If you have understood this method, then solve this problem.
Then solve this particular
So
problem.
this is a kind of text it is. So after that again if he gives the answer, then
what's the point?
He explains it so aesthetically and beautifully how the method should be. And if you then it is something like in our modern days 4-quadrant method. We give the text and make it visually available and then ask some activity based upon that to test the learning. The same method is followed. I don't see there is any difficulty in this.
Sir, you are saying something.
There is a trend of that.
Okay.
The scheme is like that. Lilavati. First of all, the rules. That is first. All the rules are in the form of sutras. Swalpaksharam, Asandigdham, Saravattam, Vishwadam. So, first of all, he gives verses in the form of sutras. Then, the solution of the problems, according to the rules, he has given problems. That means it doesn't mean that he has not given the solution and method of solution for the problems he has posed. They are illustrative examples. For details, you have to refer for the bhashya, that is commentaries written by Buddha philosophy, that is Ganesha Devadna, etc. So, the structure of ancient granthas are like that one. That point has been cleared by that matter.
I think unless we discuss the original Sanskrit text, this kind of credits Lilavati is the methodology in Lilavati.
Correct.
At least I am not satisfied with the method. If we keep on telling, okay, Bhaskaracharya tells you this is method. This is just reading it from English text.
Okay. So we'll have your way of expected way of explanation and class. Like taking my knowledge into consideration of Sanskrit and all, it is not possible for me to go into the depths of each and every word and explain like that. So with what I am able to do, I am going into the techniques which will be really useful for especially there will be some people who are looking at that aspect as well. For them, I think we'll go in this way, and for others we have that, and then of course that is available in the campus. So at any point of time, if you want to visit. Purnamada Purnamidam Purnat Purnamudachyate Purnasya Purnamadaya Purnameva Vachyate Om Shanti 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 Hari Om Hari Om.